Okay, so welcome everyone. So this is a presentation on securing 5G Open RAN with a scalable authentication, authorization, and discovery framework for XApps. And yeah, so this was an academic work done in Virginia Tech, but also in collaboration with CryptoWire Labs. Okay, so just sort of start with a quick primer. So this was intended for a non-Open RAN savvy crowd, but essentially what we have is the disaggregation of the RAN and the functionality split. We have these savvy near real-time RAN control flows and these open APIs. Now, all these new features are great for facilitating these, well, scalable and efficiency as we integrate Open RAN into 5G. However, indirectly, they also introduce these new threat actors and vectors into the 5G ecosystem. So we formulated this threat model, sort of looking back and forth between the ORAN Alliance standardization efforts. And essentially, we designated as a malicious actor an XApp that is either intentionally malicious or misconfigured due to a lack of expertise on the configurer's side, right? And the goal of this, the attack vector of this XApp would be to ultimately exploit the lack of native authentication authorization features that currently do not exist. An objective, their objective could be that they will retrieve information intended for other XApps or other RAN entities, or go so far as to even disrupt the messages between RAN entities with some sort of rogue signaling. So if we take a look at the actual propagation of the attack through this architecture, we designated some trusted and untrusted entities and made some assumptions, well, regarding the trusted and untrusted entities. Right. So first we see an untrusted MVNO, and by untrusted, not necessarily like a malicious, but can also be non-expert, making configuration mistakes that essentially instantiates an XApp on top of the infrastructure. Now, this propagates through what we have assumed to be from now the trusted backend and is onboarded. And at that point, it has access to the messages flowing back and forth in the RMR. And so our goals with this study were to propose the design and then implement and then test what we have come to call the XApp repository function framework. I'm sure that sounds familiar from the 5G core, sort of analogous to the NRF. And so the design goals were to sort of have minimal modifications to the existing standards for a more seamless integration experience. And so to that end, we kind of leveraged a key microservice design principle, which you'll kind of see soon. And so the design itself consisted of a centralized entity, sort of like a control plane, and lightweight sidecar proxy agents that would be essentially attached to individual XApps upon instantiation and provide them with various security lifecycle events. And yeah, so we actually built this, we tested it, we kind of performance benchmarked it in a production grade Kubernetes cluster to sort of show how we can meet the rigorous demands, well, the rigorous quality of service, well, latency demands of the closed loop control. Right, so before I jump into the actual design, I want to share some of the fundamentals that were key in realizing this design. First, we have Open Authorization 2.0. So this is a very well-established security standard. So it basically allows for a service provider to delegate authorization distribution rights to a middleman entity, in this case, an authorization server. So whenever a requester comes in, they would have to request an access token and then use this access token upon subsequent service requests from the provider. The token will be validated, and if found valid, the provider would then respond with the requested resource. And these access tokens come in a variety, right? So if you go into your browser and you know, those cookies that we dread so much, so what you're really dealing with in that case are these session tokens, right? So these are stored in a database on the left here. These are stored in a database, and every time you want to make authorized request, resource request, you go through a lookup, which is really not scalable for this microservice-based XApp ORAN ecosystem, right? So in that case, we have these JSON web tokens. And what these are essentially is they are self-contained units that are signed and attached to individual HTTP transactions, which a service requester would present to the service provider on every single request, right? And then these would be validated on the spot, and then the requester would be granted the service. And last but not least, in fact, I would say quite most substantial design element that we leveraged is the sidecar proxy and by extension, the service mesh. So as microservice deployments have sort of evolved, sidecar proxy and the service mesh have really become fundamental to realizing a robust design. And a sidecar proxy is essentially interconnecting agent that you would attach to your primary application, in our case, the XApp, that would provide it with non-functional requirements that the engineer itself would preferably not want to implement themselves, right? And this kind of makes it easy to update and rotate these functionalities, these non-functional requirements, as we sort of evolve in the architecture and the standards, in fact. And yeah, so all these sidecar proxies would be interconnected through this control plane, which is where the service mesh mentality comes in. So the sidecar proxy would constitute the data plane of a service mesh, whereas there would be also a centralized control plane, right? So, and this design mentality is really what we sort of, well, built the entire XRF system upon. And to sort of a little segue into why, where we were inspired, I mean, why we were inspired for this design, I'll want to sort of look into how the 5G core service-based architecture is designed. Now, if you look into specifically, I want to talk about the NRF. So if you look at the existing functionalities of the NRF, it serves as a service registry, it provides discovery and auth2 distribution. So essentially right now, a bunch of the functionalities provided the NRF have already coinciding with some of the functionalities that a service mesh control plane is supposed to provide. So if we take that a step further, if we were to, which 3GPP has, by the way, in release 16, sidecar proxy-based indirect communication between ENFs has been standardized. So if we were to take that a step further, if you were to look into popular service mesh solutions, such as Envoy, the sidecar proxy, or Istio, if we were to integrate, say, Istio into 5G core, by extension, 5G core integrated Open RAN ecosystem, it would be very, very intuitive to co-locate the control plane of the service mesh with the NRF, which already provides a bunch of the functionalities that a service mesh control plane is supposed to. So inspired by this, our design sort of took a similar approach, right? And so with that, I can just jump into it. And so here you see the overview of this XApp repository function system, right? So on the left side, we see at the top block, we see the server, which is, you might call it the control plane of the service mesh. And in the middle, you see the client, which is the data plane, or, well, XRF client, the sidecar proxy, which will be attached to individual XApps. So the server, it will serve as an XApp database, right? And it's much like the NRF for the 5G core VNFs. And this really is kind of the only standardization, well, for the seamless integration experience to work, this really is the only standardization kind of requirement, is that each XApp upon instantiation needs to generate a signed and validated, which is out of scope for now, the validation itself, a validated profile to its adjacent client so that it may actually be stored in the server. And at that point, we also have a permissions matrix, which is not only used for scope of access verification, but also conflict resolution. So basically, we want to prevent two XApps from being able to write to the same endpoint resource, which would, well, actually lead to performance degradations or actually catastrophic failures. And finally, we have this token map, which is essentially a public-private key pair mapping that keeps track of how or which specific tokens or XApps are using to access which resources, so that tokens can be revoked or renewed, well, independently from, kind of dependently between the XApp and the actual requested resource. So that is the server. And in the middle, you see the clients, which is sort of, and also highlight the flow, you see the actual security lifecycle that will be provided by the XRF client to each XApp. So upon instantiation, each XApp is injected with a client. It will then receive this profile. And at that point, this control/data plane interaction between the server and the client takes over to provide whatever requirements, whatever security requirements that the XApp will actually needs to be fully integrated into service chains. And so here's a overview of how that will look. So upon instantiation, it will create an XApp profile composed of its relevant metadata. It will then authenticate with the server, in this case, the XRF server. It will register. It will then if required to join a specific service chain, which requires multiple XApps to be communicating with each other, it will discover other XApps or even other API endpoints. And then finally request an access token in the form of a JSON web token to basically access these resources. So this is the overview of the actual message flow. And the integration itself was envisioned as a sidecar proxy that is injected into XApps that sits between the near-RT RIC and the XApp itself, basically carrying out the functionalities that we just discussed, but also serving as a reverse proxy that intercepts all messages and verifies that they are conforming to the required security verifications, and only then performing the actual functionality that the XApp is requesting. And so we actually tested this, and we kind of did a quasi integration with a service mesh solution. In this case, the linkered service mesh solution. Essentially, you see the XRF client here that is attached to the XApp as a sidecar proxy. And yeah, basically serving as an interception reverse proxy to perform these XRF server to client operations. And just to show that this is possible to synergize with the existing data planes of the service meshes, we also have this mutual TLS sidecar proxy that Linkerd sort of injects upon request. So meaning that and the reason we kind of did this was in our testing, we want to approach a production and real life environment as much as possible. And yeah, well, finally, we wrap this in service mesh control plane for various certificate management and monitoring for HTTP transactions. And yeah, so finally, we did some scalability evaluations and performance benchmarks. So our evaluations were conducted on an OpenStack cluster, on a highly available OpenStack cluster, for now isolated into the same physical host, but comprised of a reasonable number of virtual machines. And so we designated sufficient compute power to our workers so that we would not be hitting compute bottleneck in our scaling evaluations. And for the server, which would be, handling majority of the load, we even dedicated a larger virtual machine with 20 CPUs. And in the actual performance benchmark, so we first started with these user processing throughput performance. And so the idea in this is to sort of basically bombard the server with a bunch of lifecycle requests and see how it actually performs with different number of threads. And in this case, we saw that up to a certain point, and just to be clear, these are concurrent requests. So when you see 500 here, you're seeing 500 concurrent requests, which is an insane number of concurrent requests. But even up to that point, we saw that the XRF server was able to efficiently exchange compute power as the threads scaled, sort of deliver a faster processing time. And so, of course, time is important, but so we also looked at some of the CPU utilization metrics and saw that, so obviously our environment was constrained to 20 CPUs for now. But once again, we saw that there is acceptable upper bound on CPU consumption, and it really doesn't go too crazy as we start to send concurrent client lifecycle requests. And so yeah, some other more detailed benchmarks. And yeah, finally, we did an operational breakdown of our individual functionalities. And this is really sort of highlight the difference between how a client, which sits adjacent to XApp performs versus how the central server performs. And on the left, you can see the client has actually very low CPU time. And this is for 50 concurrent requests once again. So, and this sort of shows that the client, which is supposed to be distributed and deployed along each XApp, can scale, while the majority of the load is handled, when the processing load is handled by the central XRF server. So this is an operational breakdown, and sort of just to talk about the big picture of how this integrates into a very future grand vision. So here we have the 5G core, ORAN, and management and orchestration unit integration. And right now, our design is sort of, our design goal was to solely picture this XRF within the Open RAN ecosystem. But taking this a step further, in the future, well, maybe the near future, will there be a possibility of XApps having to interact with the 5G core elements? So for instance, if you're an operator and you want to introduce some custom functionality, what you do is you design an application function which is then exposed through the network exposure function. And at that point, okay, and which is an expose, and then, well, so this is essentially the introduction of, say, custom functionality. Now, with the XRF, we kind of maybe foresaw the design of an XRF to NRF interface, which would then facilitate the communication of XApps with these application functions, right? And for now, maybe this is not necessary, but in the future, who knows? Like these things are, we have a lot of moving parts, and sort of a futuristic design aspect came to our mind. And so in conclusion, we laid out the 5G Open RAN threat surface here. We developed our framework for addressing these fundamental requirements. And most important of all, we did so while trying to provide a seamless integration experience while leveraging a very, very well-established piece of microservice design principle, i.e. the service mesh. And yeah, so you can find more of this. So you can see the source code for this. It's public now. And we also published a paper on this in the past InfoCom. It's not out, I mean, we put on archive, it's not published in Actually Explore yet, but just sort of disclaimer on the source code, as the project has had a lot of moving parts, a lot of the modules in the code has been refactored, so it might not work out of the box. However, please do reach out to me personally or any other author you find on the paper so that we can kind of guide you through or answer any questions you might have. All right, thank you.
Thank you, Tolga. So I think the InfoCom isn't that just got over, right?
Yeah, it was. We presented it May, last May, in fact. Yeah, well,
right. Yeah, this is great work. So I know we have some question in the chat, but before that, I wanted to find out. I don't know if you listened to Alex's talk. So the whole RRSA activity, where IEEE uses this Open RAN industry connection as a platform to back up some ideas, brainstorm it. Then the output would be in various forms, right? The white paper, guidelines, use case document, any potential measurement results, and then some of them could be moved to standards track, right? So we are in the process of, based on today, we have about 10 or 11 proposals. We're trying to see what aspects of the presentation or the idea can be included in either in the IEEE Open RAN white paper, and subsequently can be progressed to RRSA, through RRSA to open, I mean the standards, IEEE standard.
Yep.
So what aspect of your work you think could get a berth in a standards track within IEEE?
Sure. So let me just kind of go back a little bit here.
Because there would be a security section, so we are.
Yeah, exactly. So I was about to address that. So security, obviously, ORAN standardization has some security works in progress. I would say it's actually probably the least developed part of the standardizing, the security focus group. I'm sorry if there's someone, but but I would say that's actually the least developed part of the standards as far as the ORAN Alliance work goes. However, I think they have similar plans to integrate such a security platform, but they want to do it directly on top of the near-RT RIC, which to me seems like, so if you co-locate security functionality with active runtime functionality, that kind of poses a problem, both in terms of compromising it and various types of other system level attacks, right? So because I mean, in the future, we foresee 5G and Open RAN being deployed in public clouds. Well, at that point, we expose ourselves to a bunch of these system attacks. In fact, we do have some follow-up work on that, which I can discuss in more detail with people if they're interested. But I would say that the primary thing I don't think is really appropriate in the standards right now is the co-location of this functionality with the near-IT rig. I think it kind of poses a problem in potentially integrating this Open RAN platform into a public cloud architecture. I would say that, but to sort of say which part of it would really fit in, this whole XRF system design, I think it fits in nicely, especially the seamless integration aspect would fit in nicely with standardization efforts.
Excellent. There are a few interesting questions also in the chat. I can read it for you.
I can see it, I think. So
okay.
I'll start.
You may want to tag whatever you like and maybe answer those.
Sure, I'll read it. So where did we install the VIM on? Yeah, so we did install, exactly. We installed OpenStack on 2 servers. One of the servers was a control plane. In fact, let me just scroll. So yeah, so we used 2 servers. Now we have a 6 server setup, but in this back in the day, it was a 2 server setup. So we have a control plane, control node that acts as a networking and block storage node, and then we have a compute node which basically hosts the workers. I mean, PowerPoints. I mean, I think if they're I can link my PowerPoint or send it to anyone who wants it. Yeah, orchestrator. No, if you're referring to this the orchestrator question. So about if you're referring to this big picture, we did not actually use an actual real Mano. This is just a concept drawing. We did have works like 2 years ago with ONAP. In fact, I believe the Honolulu release of ONAP back then, not OSM. But we found that the complexity at the time was too high and not really worth the effort, to be honest. And there were some buggy parts, so we kind of moved away from the Mano integration because we didn't really see too much value in it at this point for this work. And did we evaluate the incremental latency to real-time processing with incremental latency? As in, I don't really quite understand this question. We did perform well, basically we kind of did a breakdown of the we did a breakdown of the overhead. Well, in this case, you can see it for 50 concurrent requests of what you can expect to see if you want to go through the security lifecycle upon each HTTP transaction. I think it's for now for so also some of the details. Yeah, so some of the details you see here, some of the details are omitted in this presentation for more detail. For instance, especially in the access token management side, I'll refer you to the paper itself, but the average latency, well, the latency you will be experiencing is about 6 milliseconds. So not really great for super low latency applications, but now this is still application level security. The next step would be to take this into the actual kernel level security, where we use, tools like, robust tools like eBPF, right? So that will really cut down this security overhead. And if you're using Istio, right? Okay, so if you're using Istio right now, in fact, like we have ideas about forking Envoy and potentially looking into integrating all this functionality directly into Envoy. However, this is like a really down the line here, because Envoy, like there's a process, but ideally, yeah, instead of redesigning everything as a brand new solution, we want to integrate whatever is here into existing open source solutions and sort of provide it as a additional release or merge. So if you are using any service mesh, not just Istio, everything you see here is an additional functional, or should I say non-functional level, because it's a completely new layer of security that is specific to the Open RAN paradigm. I don't see any way of natively integrating with the existing auto distribution functionality in Istio. But that is, at this point, I would say more of a software engineering problem than a real design design issue. But to sort of answer the last question, I think it's regarding this. Which 5G core NFs will be, I don't really, okay, if you're using, which 5G core network functions will be Istio? I don't know, I don't understand this question, sorry, yeah. The last question.
So, I mean, are you converting all this AMF, UDR communication of the service bus
Mhm.
to an STO based communication, or
Yeah.
you are just adding it on top
Oh, I see.
for the NRF to connect to the XApps?
Right. So just to sort of, once again, that this is a concept design. This we haven't actually done yet. The actual XRF design we have done, but the 5G core part we have not done yet. But the answer to that question would be none of the communication, for example, none of the common API framework or SBI interactions would have to be changed. Essentially, in fact, like this is in Feasibility 16 is a standardized method of introducing this indirect communication. And the strength of it is that we as the, well, let's say custom MVNO, like let's say we are a small to medium enterprise MVNO, at that point, this method of attaching these SCPs to individual 5G core VNFs really enables us to sort of do custom processing on the messages by intercepting them and forwarding them back. Obviously, there's an overhead because you intercept the message and forward it back, but the overhead should be sub 1 ms. Like it will not be a terrible overhead. Well, depending on your the actual forwarding overhead. I don't know about your processing loads.
So what security problem are you trying to solve?
So in this, okay, this paper was addressed to solve the lack of fundamental security not yet integrated into the O-RAN ecosystem. The 5G core already has this, right? So I showed the 5G core to sort of see where the inspiration came from, to integrate it with service meshes and sort of explain how, if it was to be integrated with the 5G core, how the NRF could be a very good place to co-locate the service mesh control plane. But yeah,
so you are suggesting E2 interfaces to be service mesh?
No, not the E2, not the E2 interfaces.
Then the RIC,
yes,
RIC
exactly.
to the XApp?
Yes, RIC to the XApp.
But that's a programming interface. That's not really a messaging interface.
Well, so this I would say XApp to XApp communication, right? In this case, for constructing large scale, I would say service chains, we can consider using these SBI, well, service interfaces, let's say accept communication. I would, maybe I'm mistaken, but for now, this is the design that we have, and maybe it has some lower level flaws and that needs to be adjusted. But for now, this is the design that was sort of, well, proposed to address some of these fundamental issues.
I think this goes, you might want to review the O-RAN Alliance security framework.
Sure. Yeah.
And align this with that. I think I see some
overlap,
some inconsistencies.
Yeah, absolutely. No, thank you. Like we will definitely do that. And
Yeah. So I mean, this is good, right? I like at least the rigors of the paper. Very good system experimental output. I mean, we need this kind of work even for IEEE related white paper, right? You can include some of this analysis. That'll be great too.